everyone, welcome to the lecture 23 of course Climate Change and Extreme Events. So this is week 8 and we have already covered one lecture, lecture 22, where we primarily talked about two different types of models. One is called a statistical model, where we are talking about for example regression based analysis or for example ARIMA based analysis or seasonal ARIMA based analysis like that. Then we have also talked about something related to machine learning based models, where we introduce the concept of, let's say, tree based regression analysis, random forest analysis, and several different approaches where we can use it in machine learning models. We have also talked about what are the limitations and weaknesses of these two different models approaches. We have also talked about what kind of the data is required when we are implementing, let's say, statistical approach based models, and when we are implementing, let's say, machine learning based model, and what kind of the data, is it a huge amount of data we required for machine learning model. When we have less amount of data, we can go for the statistical model, but sometimes it is not true in that some scenarios where we have a very little amount of data set, and we also use machine learning models to basically get an insight about how the data is historically telling about the story. And on the other hand, when we have large data set, we can also use statistical model. So it depends upon your requirement, it depends upon what you are actually predicting. We have certain limitations with the statistical techniques. For example, when we have complex relationship, non-linear behavior, we can usually go for machine learning models like that. So in this present lecture, we will primarily talk about building and validating statistical ML based model for predictions. So we have introduced the concept in the previous lecture. Now we will use that concept to basically build that model and to understand how we can use this model for our predictions, climate predictions, extreme climate predictions like that. When we are talking about building and validating the statistical ML based model, there are few steps which are very useful, we need to have understanding about that. Data profiling, what kind of the data we are using it, whether time series data or spatial data set, or if we have using the time series data set, what kind of the variable we are using. So, and what is their sources, how we are obtaining it, whether it is coming from remote sensing data set, whether it is coming from observed data set, whether it is coming from reanalysis data set, or whether it is coming from climate projections data set like that. So there are several types of data, we have to know about those sources. Then the second step, we are essentially talked about data cleaning. Let's say we have missing data set, we can fill that gaps using statistical approaches, imputation approaches, by taking moving averages, neighbor averages, or some sort of data cleaning approaches, so that we can fill that gap. Or let's say we have inconsistencies of the years, we can make those data set in such a way that we have consistent year information for different variables, so that we can use it for our data prediction processes and data reduction. For example, let's say you have multiple types of data set and there are lots of variability which are one variable is also suggesting and another variable is also suggesting similar level of variability. How we can reduce that information with the minimum number of data points, so that our model should not be too complex, but it has certainly contain all the information from your data sources. That is called data reduction techniques. And data transformation, sometimes we are using data set with different scales. Suppose we are using, let's say, temperature data set, which can be negative and can be positive also. When we are talking about rainfall data, it is non-negative numbers above 0 and 0 sometimes. So there are so many other type of data set where we have a scale issue, where their scales are varying. So what we can do, we can transform the data, we can take normalization of the data and then make it a similar scale, and then use it for our data types of model, and then data enrichment, data validation sort of steps we basically follow to build the statistical or ML based model for any kind of a predictions purposes. So, in this lecture we will primarily talk about what are the simple steps which we have already covered in the first slide in the building the predictive models. Then we will also learn about best practices for model validation and performance evaluation. Then we will also explore common challenges in model development, and then we will compare statistical and machine learning validation, and some sort of case studies we will also discuss towards the end of this lecture, so that we can have a better understanding about in practical scenario how we can use these information, the data set and these modeling approaches and club it together to make some sort of predictive models. So, when we are talking about model development, whether it is statistical or machine learning model, there are few steps which we essentially look at. Data collections, which means we have to collect the data from different sources. It can be your point information data, grid scale data, temporal data set, spatial data set, like that. So, some data sets are temporally varying because of the at each time stamp or time step we have one value, or maybe some data sets are sometimes we are taking a static property. Let us say it could be land use land cover information, or it could be soil information, or it could be geological information, which does not change very frequently over the time, like that. So, data collection, then pre-processing, missing the gaps, cleaning and organizing the data, ensuring the quality and consistency with other variables, and what is it is required for specific type of model, whether it could be statistical or it could be machine learning based model. The third step is called feature selections. Let us say you have 100 variables and you are using those 100 variables data set to build a kind of statistical or machine learning model. We have to understand about, let us say, which variable x1, x2, x3 to x100 has more importance in predicting y compared to other. So, it kind of a feature importance we are taking about relative importance of different variables. Let us take example. When we are talking about, let us say, discharge and rainfall relationship, rainfall, soil moisture, evapotranspiration or similar type of data sets are important because they are somehow interfering the hydrological runoff generation processes and can also modulate the flood peaks in a certain region. Therefore, when we are talking about flood peaks modeling, drought analysis, these kind of data sets are relatively important. That is called feature selection or data selections, like that. Once we have selected the important data set, we have built the model, then we will try that model for training purposes. So, what we will do essentially, we will divide our data set into 70% and 30% or 80% and 20%. Let us say you are taking 80%. So, 80% part will be used for training of the model. What do you mean by training? Basically, we are trying to specifically obtain the model parameter where that model will converge. Okay. So, that is the model parameter we will obtain from the 70 or 80% of the data set. Once the model has been fixed with your 80% data set, then we can use the remaining 20% of data set to predict or to check the accuracy of your model predictions. Why it is important? Because we have not revealed that 20% information to the model when we are developing that model in the beginning, and therefore, that is kind of unknown 20%, and then we have used that 20% to check what is the accuracy of our model data. So, that is called model training, then performance evaluation, and using that 20% of data set we can evaluate what is exactly our performance of the model. So, these are some of the very basic steps which generally follows in all of the modeling, data driven modeling processes in climate science and other fields as well. So, when we are talking about so when we are talking about statistical model development, we have talked about in the previous classes that linear regressions, logistic regression, ARIMA type models, generally we use it. So, what is the assumption and consideration in these types of model? We are assuming some sort of data distribution assumption. We are assuming that data is behaving like a certain types of distribution, whether it is normal distribution, log normal distributions, or some sort of different types of distributions. And then we also look at the multi-collinearity issues, where we are looking at whether multiple the variables, or we are using it that variables are also correlated with each other. That is also we have to check when we are building that model. That can also create some sort of problems when we have some sort of multi-collinearity issue with the data set. So, this is a simple example of linear regression, where we have x value, then we have y value, and that basically can model it for these types of data set that predicts a continuous output by modeling a straight line relationship between input features and target variables, such as estimating the impact of price change or demand, or let us say rainfall or runoff, or let us say heat waves and temperature, like that. Logistic regressions are the model which basically predict the binary outcomes, whether that particular event is going to happen or likely to happen or not, 0 or 1. So, that is called the logistic regression analysis, where we are looking at the true and false or binary output of our the target variable. Then we have polynomial regression, that is kind of a polynomial fit with our data set, where we are looking at impact of multiple different types of relationship with this kind of the data. Then we have also time series regression, where we are looking at the time series data set. We are also retaining the information of each time steps, and then we are modeling it. That is we are calling it time series regression, or support vector regression is another type, where we basically look at multiple different types of variables with their regression analysis, like that. In the machine learning model development, we can use multiple different models, let us say decision trees, random forest, gradient boosting, or neural network, or the neural network, MLP, CNN, or long short term memory models can be also be used. Then it basically go into the machine learning model development, data processing, then data cleaning, then your model development, then training of the model, then testing of the model, like that. Once it is done, then we also apply some sort of optimization technique. Suppose in the training of the data set, when we are revealing 70% or 80% of the data set to the model, we are essentially trying to search the correct value of the parameter which is involved in this kind of model, and then we use that parameter to basically build that model. So, to search those parameters, we use some sort of optimization techniques, which could be your hyperparameter tuning, or which is a terminology used in the machine learning domain, where we are trying to find out different parameter values using some sort of optimization techniques. What are those techniques? It could be your grid search, where we are looking at different values of the parameters. Let us say there are 3 parameters A, B and C, okay, and now you have A, you assign that A can be 1, 2, 3, B can be, let us say 10, 20, 30, and C can be 100, 200 and 300, like that. So, there are multiple combination can be possible of A, B and C, and for each combination we try to search the model output, and we compare with our 70-80% data set, and then check our accuracy of the data set. Whichever combination of our parameter gives you the best accuracy, where that model will be stopped, and that is called your hyperparameter tuned model and optimized model for our analysis. Then we have a random search model, a random search parameter hyperparameter tuning techniques, where we are not looking at sequentially of all the combination, but we randomly search from one place to another place, and wherever we are getting the highest accuracy, then we minimize our search domain into that particular region, and then we check that particular regions, like that, where we are getting the good accuracy of the model, like that. Then we have Bayesian optimization, where we are looking integrating the probability and Bayesian approach with our optimization technique, and then we are trying to find out the parameters of our model, and then we use it for our prediction purposes like that. So, building a ML based model, we have certain different steps. For example, exploratory data analysis, where we are talking about data attribution, data cleaning, data pre-processing, then feature engineering, finding out the most important data set. Building the ML model stage, we are trying to look at the training and testing of data split. When we try to choose the best appropriate ML algorithm, then we basically build the ML model with the training data set with the 70 and 80% data set. Then using the third step, our model development is tuning of the model parameters, where we are evaluating the model with the test data set. Then we compute the performance, and then we do some sort of hyperparameter tuning and repeat that step when we are getting the best model, and then we basically go to the final step, which is called the ML model selection, when we have iteration and then we have choose the best ML model for optimize performance, and that model we will use for the prediction purposes like that. So, in the ML model approach, this one important aspect is feature engineering and feature selections, which is basically why it is important, because let us say you have 100 number of data set, we have to search our domain in the best appropriate variables, which basically can define the behavior of your target variables like that. So, that is we call the feature engineering and feature selections. In this feature engineering and feature selection, there are several techniques. One is called principal component analysis, where we are looking at different principal components, and then basically we try to reduce the dimensionality of the data set by selecting PC1, PC2 and PC3 most of the cases, and that basically represent 99% variability in your data set. So, suppose you have 100 variable in your data, and you are now, when you are applying the principal component, you are converging your data variability into 3 variables like PC1, PC2 and PC3, and that basically explains the overall variability of behavior of your target variable. That is called principal component analysis for feature engineering and feature selections. Then we have recursive feature elimination. That is basically a method which basically remove one by one variable at different iterations, and basically stop when we have a relatively higher predictive power or accuracy of the model. That is called recursive feature elimination algorithms. Then we have domain knowledge based selections. Suppose we know the behavior of the target variable, climate extremes, and we know that these climate extremes are related to temperature. Let us say this is heat waves, this is related to temperature, humidity, wind speed, etc. That is called the domain knowledge, because we know that the target variables are related with multiple different variables based on some physics law, some meteorological principle like that, and that is we use it for selecting that different types of input data set. Then once we have done this feature engineering and feature selection, we try to look at feature importance ranking. So, that is basically we try to rank all these variable which we are using it for modeling the target variable, and then we are ranking it, and then we are selecting the best ranked the variable for our model development. So, this is called the feature engineering and feature selection method, where we are essentially trying to optimize our data set by using some sort of different approaches, so that we can have a minimum number of variable that cannot make that model more complex. However, it has a limited number of variable that can basically explain the overall variability of your target variables like that. In the model, when we are talking about, let us say, a statistical model and the machine learning model, the important after this feature selection step, the most important thing is your validation technique. What kind of the validation technique you are using, how you are validating the model, because if you have the best validated model that has the minimum uncertainty, minimum error, and when we are using that kind of model for your climate projections or future projections of your climate extremes, that can give you the more reliable results of climate extremes like that. So, therefore, validation of your modeling, whatever the model we are using it, it is very important for sort of model development. So, what kind of the validation techniques we have? We have cross validation methods, which is called k-fold cross validation algorithm, and there is we call leave one out cross validations, LOOCV, that is another cross validation method. Or we can also have a resampling techniques, which is basically used by bootstrapping for robust evaluation. We can generate random samples based on bootstrapping, resampling, and then we use it for our model evaluation. So, here it is a k-fold cross validation algorithm is, let us say this is your training data set and you have test data set. Now, what we can do at different folds, let us say you have this much amount of data and you have divided your data into 5 different portions, equal portions. So, at each iteration you are basically removing one validation part, removing that part and using it for your validation purposes. So, for example, you running the model for training data, this one and that one, and then using it for your validation purpose. In the iteration 2, you are using training data, this one and that one, and then using this data set for your validation purpose. Similarly, you are using this for validation purpose, and for fourth fold you can using for this particular purpose. So, here you are dividing your data set into 4 folds and then you are basically using it for different types of, it can be n fold, it can be 100 fold also, and for each fold you are using one part of the data set completely unknown to the model, and the 3 remaining testing data set is used for your training of your model. So, you have at the end for this particular case example, you have model 1, model 2 and model 3 and model 4. So, what we essentially do when we are looking at these types of fold based or k-fold based cross validation, you have different models for different folds, and therefore, you take the ensemble mean of all these parameter values that can be represent your overall ensemble model of your k-fold validation techniques like that. So, that is the final validation loss we are dividing by 1 by 4, which is number of folds divided by value by taking the total validation loss by different steps, adding it, and then we are taking the average out of it. So, that is basically how we can use it for k-fold cross validation techniques like that. Similarly, leave one out cross validation also works, where we are removing one part of the data and then we basically use it for training of our models like that. Why it is important? Suppose you have less number of data set in our model development phase. So, when we have less number of data set, we can use these types of techniques to increase our validation power with our data, not to rely upon only one set of the data, but entire set of the data, and then we can build our models like that. Then the third important thing is about the model development is performance matrix evaluation. Suppose we are developing some sort of regression based analysis statistical model, we are talking about R square, correlation coefficient or adjusted R square, RMSEs, root mean square error, AIC and BIC criteria like that. Or let us say we are talking about some sort of time series model, then we are using MAPE, mean average error, then root mean square error, that like mean absolute error. So, that is basically we use it for our time series model evaluation. Then for the machine learning model, we use accuracy, precision, recall, F1 score and all these different matrices to basically look at what is their the overall performance of the model. So, this particular figure gives you a more detailed overview about when we are talking about the regression analysis, we are talking about MSPE, MSE, R square and adjusted R square. Then if you are talking about classification, then precision recall, ROC, AUC, accuracy and log loss. Then unsupervised model, RAND index, mutual information, or others we can basically use CV error or heuristic methods to find, or blue score or NLP when we are using it like that. So, these are some of the matrices why this basically can give you an idea about what is the overall accuracy of the model. For example, if you are talking about R square, if your R square is greater than 0.2, 0.8, 0.9, which tells about that your model is highly accurate when we are comparing with your observed and simulated data sets like that. There is another problem with the modeling step is basically overfitting and underfitting. Sometimes when we are dealing with the accuracy assessment, it is possible that our model is overfitted and therefore it is basically not very reliable for predictions, or maybe underfitted. It is too simple and therefore lacks predictive powers. So therefore we use some sort of regularization schemes L1 and L2, and that is basically regularize our overfitting and underfitting problems in our machine learning, or let us say we can improve that overfitting and underfitting problem with using of the entire or cross validation scheme, where we are exposing entire data set for our validation purpose and eventually we are using it for ensemble mean of the data set. So that is basically example of underfitting, that is example of overfitting, and this is how basically our data or our model should behave, that is called optimal. So we use all these different algorithms to basically restrict the behavior of model, so that it should not go into the territory of the underfitting, or it should not go to the territory of your overfitting model. Then the another important area is model interpretability and explainability like that. So explainable AI are generally used to techniques that help us to trust and interpret the outcomes of a machine learning model and deep learning model. There are several techniques which can be used. Suppose here we have multiple different variable when we are developing the models. We can use SHAP value, and then we can use it to look at how the different the parameters or variables are relatively important compared to other values like that. So that is basically can give you an idea about whether it is explainable or interpretable using these kind of the variables like that. So this is how basically we develop the machine learning or statistical models based on certain criteria. Now we will talk about some sort of case studies where we will focus upon how we can use this model for prediction of climatic streams. So the first case study is validating a heat wave prediction model. So what we are using, we are selecting some sort of input variable, maximum temperature, minimum temperature, that we are talking about the mean daily temperature, and based on that we have defined some sort of excessive heat index, heat stress index, and that is basically when we have used it, making it some sort of factor or some sort of analysis, and entering into some sort of machine learning or AI based model, and then we are generating the output based on our whole data set, and then we are projecting it for your spatial scales like that. So the major objective of this particular case study is to predict the extreme heat events. Here we have used the cross validation technique with the historical data set, and then we project basically we try to predict the model behavior, which tells that it has been improved accuracy over time series if you compare to the baseline scenario. So means we are able to predict the heat waves in future time steps as well using these kind of the models. Then case study 2 is flood risk assessment model, where we are using different types of data set, NDVI, elevation, aspect, curvature, slope, rainfall frequencies, flood layers, distance to the river, flood roads and drainage. We basically use data set into a certain type of normalization technique, so that all the data set should behave in a similar scale, and that is basically we can use it for our machine learning modeling. Before that we also check different types of multi-collinearity and training and validation of samples, and then we use the feature influence, and then we use some sort of modeling validation, and then we try to generate the flood risk maps based on this kind of the assessment model. So this basically tells about using the appropriate input data set, we can also predict the spatial scale of the flood risk across different regions based on some sort of machine learning AI based tools like that. What are the challenges in model validations? So, when we are talking about validation, sometimes we have the missing data set which can create some problem, or imbalanced data set. Let us say you have more outliers or more lower values or more very high values, that can sometimes create problem in your validation of the model. Computational complexity, sometimes we have large scale model that requires more number of data points, more computational resources. Therefore, it is basically sometimes a kind of a limitation with our data set model. Or let us say we are talking about generalization issues, ensuring the model robustness across different database. So, what are the top challenges in deep learning or machine learning is overfitting and underfitting, that is the one problem. Or let us say we are talking about data quality and quantity, computational resources, interpretability, or we are talking about, let us say, hyperparameter tuning. If it is not parameter tuned, then it is possible that our model will not be able to perform very good and can give you some kind of error. Scalability, let us say you have developed the model for very small scale area, and it might not be possible to replicate the similar model for the other region or bigger regions like that. So, that can basically create some sort of problems or limitations. Ethical and bias issues, hardware limitations and adversarial attacks, these are the some other challenges when we are talking about model validations like that. So, what is the best practice for model development or building? Ensure data quality, clean, pre-process and standardize the data set, select appropriate model. We have to use the consider complexity, interpretability and accuracy. Based on that, whether we have to go with the statistical model, machine learning based model, or more complex AI based models like that, or use proper validation techniques, because if we do not use a robust validation techniques, we might end up not reliable climate or predictions results from that particular model. So, therefore, we can use the cross validation, regularizations and uncertainty quantification techniques, so that we can have a better understanding about our model predictions power using that data set. So, what is the overall summary of this particular lecture is, we have talked about detailed about different types of models which are statistical and machine learning based model, and we have also talked about their differences as well. We have also talked about how we can basically use these modeling framework to develop a full-fledged prediction model for a certain region. For that, we need some sort of important steps. For example, validation techniques, data cleaning, data pre-processing, like that, it is very important. Then we have also talked about explainability and interpretability, that basically can improve model trustworthiness when we are using it for multiple different areas, multiple different purposes, or let us say we are developing that model for bigger regions or for longer time series like that. So, that is basically we try to look at those data set as well, models as well. So, in the next lecture, we will primarily talk about scenario analysis using whatever we have discussed in this particular class, the development of the model, we will apply it, and then we will try to look at the scenario analysis and projection of the future extremes, how we can do for the let us say climate extremes for the future scenarios as well. Thank you so much for your attention.